Yeah, so next Tuesday is a rescheduled class day for the Friday classes. So today would be the last day for classes. I mean, for my classes, effectively. Now, here is something we discussed in my last class is that since I thought that Tuesday would be the last day, I planned to do Green's theorem on Tuesday. Now, what I can do is I can record a lecture and upload on YouTube and give you the link on eCampus as I do. So you can listen to the lecture and then we can discuss something on Tuesday. I mean, the class hours on Tuesday would be some sort of an office hour. So I'll be around and then you can come and ask questions about the lecture, or I'll post a sample final on Sunday or Monday, I think. So that's one option. Or other option is that today would be the last day and then whatever we do today would be the syllabus. And I'll post a practice final anyway. So let me know by, let's say, end of Saturday. Let's fix end of Saturday. Let me know what you want. So send me email. So you can coordinate among yourselves and let me know what you want. So either way is fine. I can give a pre-recorded lecture and then upload on YouTube, or I can just end today. So that's more or less the plan. Yes, exactly. So I was planning to announce on eCampus anyway. The finals would be on the actual time. So the actual date and time. So for section 501, so section 503, so this class, it would be May 4th. So it's a Monday. So Monday, a week after next Monday, from 1 to 3. So let me write it here. So section 503, this is Monday, May 4 from 1 to 3 p.m. And the previous section, 501, that would be Tuesday, May 5th, and the time is same, 1 to 3 p.m. Okay, so that is the timing. So what I'll do is I'll set up two Zoom meetings on this date and time, and you have to give synchronous exams on these two dates. But the pattern of exam would be more or less, you will have some computational question and you will have some multiple choices where you need to explain the choice. And once you are done, let's say after 3 p.m., I will give you a window of maybe an hour. So between 3 and 4 p.m., you will be asked to upload your exam, just like the previous take-home exam. I mean, you have this limited window, let's say from 3 to 4 p.m. to upload the exam. So all these details I will announce over the weekend. So is it clear, more or less, what's the pattern? And let me know about this pre-recorded lecture, so I can do both. I mean, I can either end today or I can give a pre-recorded lecture and upload on YouTube. Okay, but let's begin today's class. So let me connect to my iPad. And that is something. So today this has been a recurring issue. So sometimes it gets disconnected. Let's try again. Just a second. Once more. Eventually it will work out. I think now everybody is using this format, and there's a huge load on the internet, I'm guessing. Okay, what's going on? Just another try. Okay, let me restart my iPad and see if it works. Just give me a second. So your classes are mostly done, or you're still left with some other classes? So how are the other lectures going on? So the profs are still sticking to the whole syllabus? They're demanding a lot, or? Okay, let me try now. Yeah, I mean, they should be reasonable. Okay, good. Good. Finally. Zoom polling. Oh, ouch. So what is Zoom polling? Whether to have an exam or giving the exam by poll? Asking maybe Donald Trump to let you give the exam or something like that? Anyway, but can you see the whiteboard now? Zoom has a polling max. Oh, I see. Okay. It has a max 10 multiple choice. I see. Well, then, I mean, he or she has to work less in grading. I mean, exams, the take-home type exams are extremely difficult on the eyes. I mean, they take a toll on your eyes. Oops. Okay, so today we will do computation of double integrals. So that's the topic. So what we do is to define some nice domains where we can solve our double integrals and do some examples. That's the agenda. And according to lecture notes, it's VC7 and VC8. That's what we are covering for today. Okay, so we define, let's say, nice domains that's the first task, to define nice domains where you can compute integrals. So that's the first definition. Okay, so our region D is called, let's stick to the lecture note. D in R2 is called elementary domain if it is, so there are three types. Type 1, so type 1 D can be described in the following manner. So your x coordinate varies between two fixed numbers, while the y coordinate varies as a function of x. Okay, so if you draw the picture, it will look like the following. So you have x equals a and x equals b. So these are the two fixed lines within which the x coordinate varies. And then you have your y varying between gamma x. So y equals gamma x and y equals, sorry, is y. Y equals delta x. So these are, so this is type 1. Now type 2 is when you vary your y between two constants. So type 2 is you take your y between two fixed points C and D while vary your x as a function of y. Okay, so just to make this remark, why does this keep happening? So here gamma x and delta x, they are continuous functions of x. So they're nice enough functions between which y varies. Similarly here, your alpha y and beta y are continuous and infinite, if you want to, infinitely differentiable functions. So nice enough functions between which x varies. Okay, so once again, in terms of pictures, you have these two fixed lines between which the y coordinate varies, and then you have your x as a function of y. So this is alpha y. So x equals alpha y and x equals beta y. Okay. So this is my region. So this is D here. This is my D here. And finally, type 3. If x, or not x, sorry. If D is both of type 1 and 2. So sometimes a region can be both. So it can be delta x is just an arbitrary function. Yes, I mean all of this gamma x, delta x, or alpha y, beta y, these are functions of x and y, arbitrary of course, but you don't want too much variations. Let's say you want them to be nice enough functions, so that's why you can restrict to, let's say, continuous functions, or if you want infinitely differentiable functions, but they're functions. Yeah, they're arbitrary functions. Okay, so type 3 if D is both of type 1 and 2. So sometimes the domain can be both of type 1 and type 2, as in this example. And this is the most obvious example one can have. So consider D the unit disk. Okay, so this is, oops. Terrible picture, but you get the idea. So this is my open unit disk, and this can be viewed both as a sorry, both as a type 1 and type 2 region. So as type 1, D has this description. So you vary your y coordinate between root over 1 minus x minus root over 1 minus x square and root over 1 minus x square, of course, since this is the point. So x square plus y square is less than or equal to 1 means y square is less than or equal to 1 minus x square. So minus root over 1 minus x square less than or equal to y. Okay, and the other way around. So x square is less than or equal to 1 minus y square, etc. Okay, so y varies between minus root over 1 minus x square and root over 1 minus x square, while your x varies between minus 1 and 1. And as type 2, it's just the same thing with respect to y. So xy in R2 such that root over 1 minus y square less than or equal to x and minus 1. Okay, so D is of type 3 here. Okay, and domains in general can be of type 1 only, type 2 only, but most of the cases it would be of type 3. So you can consider it as both type 1 and type 2, or sometimes it might happen that a domain can be a sum of or a union of different types of elementary domains. So let's do this here. So sometimes a domain or a region can be an union of different elementary domains. Okay, we will look at an example later when we do the computations, let's say. Okay, but keep this in mind that domains can be of type 3, or it can be an union of different elementary domains. Now, here is the point about calculation. And I will state all of these as facts. So facts 1, well, before 1, let D be an elementary domain. Okay, let D be an elementary domain. Then this is the first type. If D is of type 1, then elementary domain, and let's say F is continuous and bounded on D. Okay, so F is double integrable on D. Then the double integral of F in this domain can be computed as this iterated integral. So you integrate first this function as a function of only y, so along the variable y, with these two endpoints, so gamma x and delta x. And the resultant will be a function completely depending on x, so that you can integrate along the x-axis. Okay, so you'll get a final answer through these iterated integrals. So if it is of type 1, then one can show that this double integral is same as this iterated integral. And if d is of type 2, then the other way around. So the double integral of f is given by first integrating along the x-axis, keeping in mind that the x varies between these two functions, alpha y and beta y. So fxy dx dy, and now vary y between c and d. Okay. And the third type is something which is most important. If, in some sense, if d is of type 3, then one can show the following. One can show that for any, let me form this correctly, any characterization of D as a type 1 region, let's say D1, and another of type 2, oops, let's call that D2, we get the following, that the double integral of f is either given by considering it as a type 1 region or as a type 2 region, and they're the same. So this is the result. So what was the range? Gamma x to delta x. Oh, we don't have gamma or delta here, so we don't need it. D1 of FDA. So this is as type 1 region, and that is same as considering D as a type 2 region. Okay, so it will give you the same answer. So this is the version of Fubini's theorem for elementary domains. Okay, so you can choose D either as type 1 or type 2, and then depending on how hard it is, you can solve one of these two integrals. Okay, and we will see later an example where this characterization of D as type 1 or type 2 is really important, in the sense that choosing it as type 1 or type 2, you may or may not be able to solve the integral. Okay, so characterizing it correctly is very important, and I mean the correct characterization comes from doing more and more problems. And oops, yeah, if the following happens, that if D is an union of elementary domains, then the integral along D is the sum of the integrals along each of these DIs. Okay, so sometimes this might also happen. The one I was talking about previously, that sometimes a domain or a region can be an union of different elementary domains. So in that case, we have that the integral on this domain D is the sum of the integrals on this elementary domain. So this uses one result from, or one property from double integrals. Okay, so these are more or less the exhaustive characterizations of how to compute double integrals. So let's do some actual computations now. And we will stick completely to examples that are there in the lecture notes. So problems. So D is the region bounded by the parabolas y equals 3x squared, then y equals 4 minus x squared, y-axis in the first quadrant. Okay. So this is the question. So find the double integral f dA for f for this polynomial function. Okay. Now, the most important thing about all of these problems is to draw a correct picture, which will give you an idea of what to consider or what type of domain this D would be. Okay, so in this case, you have two parabolas. One is this one, so y equals 3x squared. So this is one parabola. So you just need the approximate shape. Don't bother about accurate diagrams. The other one is y equals 4 minus x squared. So it will be something like this. Okay, so this is y equals 4 minus x squared. And they intersect in the point 1, 3, at the point 1, comma 3 in this first quadrant. And how do you find the point of intersection? You just equate the y coordinates. So y equals, so this can be found in the following way. So equate y equals 3x squared and y equals 4 minus x squared. So 3x squared equals 4 minus x squared means that x squared equals 1. So x is 1 or minus 1. Now we discard the minus 1 because we are considering only the first quadrant. So we have x equals 1. So this is discarded. Since, okay, so this is my D, just to make sure. Since D is in the first quadrant, and plug in x equals 1 in any of these two equations. So we plug in the y equals 3x squared to get y equals 3. So this is how you get the point of intersection, 1, comma 3. And okay, so something else, 1, comma 3. So this is 1, comma 0. And this point, well, the drawing is terrible, but this point is actually 2, comma 0. It should be a little bit farther away. Anyway, so we have enough characterization. So now can you tell me which type of domain this D is, or at least the easiest way to see D as a certain type 1 or type 2? So any ideas? So what should be the range for X? Type 1, yes. Yeah, so type 1, that's correct. So what should be the range for X? So D can be viewed as type 1. That's correct. 0 to 1, yes. So equal to, so let's write it down. So X is varying between 0 and 1. And what about Y? Y varies between, not between 0 and 4, but as Ernesto tells me, between 4 minus x square and 3x square, but the other way around. It actually varies between 3x square and 4 minus x square. So 3x square less than or equal to y less than or equal to 4 minus x square. Okay. So that's our type 1 region. And once we have nailed down the type, the rest is just solving the integral. So this integral d of f dA, so this is given by, so first you integrate along 3x squared to 4 minus x squared, and then along the x-axis from 0 to 1. So f is given by x square y, so x square y dy dx. So this is my integral. And each one of these integrals is easy to solve. So first we solve this integral. So this is 0 to 1. Then this is x squared y squared over 2, varying between 3x squared and 4 minus x squared dx. So this is equal to 0 to 1, x squared over 2, then 4 minus x squared whole square minus 3x squared whole square, which after some hard computation will come out to 8x squared minus 4x to the 4 minus 4x to the 6 dx. And again, all of these are polynomials, so it's just fundamental theorem of calculus, which you can apply to get the final answer. So this is the final answer, okay? Now, here is one thing I want to point out regarding all of this type of problems is that setting up this region D as either type 1 or type 2 or type 3, that will carry some points. So that will be an important part of the problem. Next is setting up the integral, which will carry more or less the rest. But I don't bother about the final answer. That's what I keep repeating. I mean, it's not an exercise in solving integrals. Rather, I mean, integrals you can solve just by feeding to a computer. What I want you to do is to set up the domain correctly as type 1 or type 2, then set up the integral and solve as much as you can. If you're stuck, you're stuck. I mean, don't bother about solving it completely using some like wasting your time solving the integrals. So concentrate on finding the domain or the type of domain and then setting up the integral. So these are the two main steps that I want to see. Okay, so this was more or less straightforward. Let's do the next one, which is also straightforward, just that it involves something called change of variables. So now let D be the domain. Given by a picture, given by this picture. So you have 1, so 0, 1, then 1, 0. Then you have this line. So this is x plus y equals 1. So D is the domain in between. Okay, now once again, and your f, the function, is given by 1 minus x minus y, okay, from t to r. Now, what type of domain you think D is? Type 1, type 2, or type 3? Sorry. Yep, type 3, exactly. It's very symmetric. I mean, you have this line x plus y equals 1. From here, you can express either x as 1 minus y or y as 1 minus x. And your y varies between 0 and 1, and your x varies between 0 and 1. So it's fairly symmetric. So as you have said that it's a type 3 region. So you can view this. So D is of type 3. Okay. So as type 1, D can be written as follows. So you vary x between 0 and 1 and vary y between 0 and 1 minus x. That's it. Okay. And then you solve this integral. So this is 1 minus x minus y dA. So this is given by integral 0 to 1, then integral 0 to 1 minus x, 1 minus x minus y dy dx. And once again, this is not so hard. Everything is polynomial. So 0 to 1 y minus xy minus y square over 2, varying from y equals 0 to y equals 1 minus x dx. So this is 0 to 1, and you get this function of x completely. And once again, everything is polynomial, so you can use the fundamental theorem to actually get this answer. So this is given by integral 0 to 1. So 1 minus x whole square over 2 dx. So if you compute all of this, so this is minus 1/6, 1 minus x cube. So this is from 0 to 1. This is 1/6. Okay, so this is the final answer. Now, as type 2, it's just the same idea, just you replace x with y. So as type 2, so 0 less than y less than or equal to 1, 0 less than or equal to x less than or equal to 1 minus y. So this is as type 2. And now if you formulate this problem as type 2 region, so this is simply 0 to 1, 0 to 1 minus y now, then 1 minus x minus y dx dy. Okay, and of course from this fact, this particular fact, you know that they will give you the same answer, viewing it as type 1 or type 2. But even otherwise, without going into that fact, you can just see here that if you replace x, if you exchange x and y, you will get exactly this particular integral. So just replace x with y. So it is a very simple example of change of variable. Okay, and hence the value will be exactly same as this particular integral. Okay, so using a very simple change of variable, namely, oops, namely x going to y, we get that this integral 0 to 1 minus y is same as the last one. So this is 1 minus x minus y dy dx, and the value is 1/6, of course. So sometimes even without going into that heavy machinery, you can say that the two integrals would be same. For example, here just using the simple change of variable. Okay. Any questions about this one, number 2? Okay, if not, then let's carry on. So as I was saying that not all domains are of type 1, type 2, or type 3. It can be a mix. So there would be domains which is a union of elementary domains, which is an union of elementary domains of several types. And then to compute the integral, you just take the sum of the integrals along each elementary domain. Okay. So let's see one particular example. So example of a domain which is an union of elementary domains. Okay. And the example is pretty familiar. It's the example of annulus. So you take the region between two concentric circles. Okay, so let's see. So this is x squared plus y squared equals 1. And the outer circle is x squared plus y squared equals 4. So this is radius 1. And the outer one has radius 2. And this is your d. Okay, so this is my d. Okay, so d is the annulus. Given by this equation. So 1 less than or equal to x squared plus y squared less than or equal to 4. Okay. Now, if you think a little bit, you will see that you cannot categorize D as either a type 1 or a type 2 region. Okay. Just from the nature of D. But there is a particular way to view D as a union of elementary domains. For example, what you can do is the following. So let's draw this picture. Okay. Now consider these two regions, the upper part and the lower part. So, well, let's call this D1 and this is D3. I mean, just to name them. Now, these two are type 1 domains. So for example, D1, so what are these points? So this is root over 3 comma 1. This is minus root over 3 comma 1. Same here. So this is root over 3 comma 1 and this is minus root over 3 comma 1. Okay, so then D1 is given by the following range. So xy in R2 such that your x varies between minus root over 3 and root over 3. Okay, and all the while your y, it varies between 1 and root over 4 minus x squared. So 1 less than or equal to y less than or equal to root over 4 minus x squared. Okay, and D3 is the symmetry along this x-axis. So here x comma y in R2, then same thing, x varies between minus root over 3 and root over 3. Oops, yeah. And in this case, y varies between minus root over 4 minus x squared and -1. Okay, so these are the two regions, or these are the two elementary domains of type 1. So D1 and D3 are of type 1. Okay, so D1 and D3 are of type 1. Now, we are left with the portion which is not shaded. Once again, terrible drawing, but just bear with me. So here you have these two portions. Okay, so this is D2, let's say, and this is D4. And these two are of type 2 regions, or are of type 2. Okay, now what is the classification? So D2 is given by x comma y, such that now y varies between -1 and 1, and all the while x varies between √1 minus y square and √4 minus y square. Okay, and here once again it's the symmetry along the x-axis. So this is x comma y. As usual, y varies between -1 and 1, and x in this case varies between minus √4 minus x square, y square, and minus √1 minus y square. Okay, so these are the two type 2 regions. So D2 and D4 are of type 2. Okay, now, oops, sorry. What's going on? Okay, so now you have written D as a union of these 4 regions. So D1, union D2, union D3, union D4. And hence, given a function, so given a continuous function, we get this integral as the sum of these integrals along the elementary domains. Okay, now depending on the function, the integrals can be simple or it can be very hard, but at least you have this description of this domain as this union of 4 elementary domains. Now you can be a little bit you can, if you know a little bit about polar coordinates, you might say that why do this? I mean, in polar coordinates, this annulus has a very simple description. So I will make a remark here and ask you to see the note on polar coordinate. In polar coordinates, D has a much simpler description. Namely, you can just say that, so r and theta, these are the two coordinates in polar form. So r varies between 1 and 2, it's the radius of the two circles, and theta varies between 0 and 2 pi. So that's it. So that's the description in polar coordinates. But this very simple description can be a little bit deceptive, in the sense that this very simple description may have very little information. So given a function f, you might be able to begin the integration with respect to polar coordinates, but with this very little information, it might be impossible to solve the integral. On the other hand, if you view this as a union of these four regions, although you have to solve four integrals, but on each elementary domain, the integrals might be simple enough to do. So, I mean, there are trade-offs in both. So viewing this as polar coordinates, the description of the domain is simple, but the integrals might be tough. On the other hand, viewing this as a sum of, or the union of these elementary domains, individually the integrals might be simple. So depending on the function, that is. But once again, I will say that you are free to use the polar coordinate description, and you can solve the double integral using polar coordinates if it is simple enough. But I won't ask you questions specifically on polar coordinates. Okay, so that's not included in the syllabus, but I mean, if you are familiar with it and if you study the notes, then you are free to use it. Okay, so there is one more problem in VC7, which I am not going to solve. It's about a parabola and a line. So you have a domain which is surrounded by a parabola, x equals y square minus 2 and x minus y equals 0. And you are asked to solve a double integral. So this is something which I leave for you. It's completely solved in the lecture note. And I move over to VC8, where we will look at an example of splitting up a domain into elementary domains. Okay, so this is on page 3 of VC8. Okay, so this is an example of breaking up a domain. Well, the previous one is an example, but here we will actually solve an integral into so this is the problem. Let D be the triangle. So it's a triangle with vertices 0, 3, 1, 1, and 5, 3. So these are the three vertices. Then compute the integral d of f dA, where f of xy is given by this polynomial, so 6x squared minus 40y. Okay, so this is my function. Now, once again, drawing the picture is the most important thing. So drawing this triangle correctly, so you have 0, 3, then you have 1, 1. So let's say this is 1, 0. This is 1, 1. Okay. And then you have the third vertex is 5, 3. So let's say this is your 5, 0. This is y equals 3. And this is your third vertex, 5, 3. And this is your domain. So this is my D. Okay. Now, the first two things you need are the equations of these two lines. So we need the equations of the lines passing through 0, 3, 1, 1, and 1, 1, and 5, 3. Okay, so number one, so passing between 0, 3 and 1, 1. So the tangent of the slope is minus 2. So the equation is y equals minus 2x plus 3. Okay, so this line is y equals minus 2x plus 3. And what about the second one? So number 2, passing between 1 comma 1 and 5 comma 3. Once again, the tangent of the slope is half here. So the equation is y equals half of x plus half. Okay, so this is the equation. So y equals half of x plus half. Now, before splitting this up in elementary domains, I make another remark here. So you can very easily view this this domain as a type 2 domain, okay? Because y varies between 1 and 3. So y varies between 1 and 3, while x varies between these two lines, okay? So it is simple to view D as a single type 2 region. Namely, your y varies between 1 and 3, while your x varies between the two lines. So let's see. So it is minus half of y minus 3 less than or equal to x less than or equal to, oh, this is the other one, 2 times y minus half. Okay, so this is as type 2 region, if I did my computations correctly. So this is simple enough. So this is a single type 2 region, and you can compute your integral using this type 2 region. So maybe I'll leave this as an exercise. Compute this integral, oops, not this d. Using the above description. But here, what I'm going to do is to view this as a union of two type 1 regions, okay? To do that, let's see how it looks like once again in pictures. So let's use the same picture. So what we do is to view D as a union of these two subrectangles, D1 and D2, okay? So D1 has this shade and D2 maybe has this shade. So these are my two triangles, and we write D as a union of D1 and D2. And how does D1 and D2? So we view D as a union of two type 1 regions. Namely, D1, so D1 is given by x comma y in D such that x varies between 0 and 1 and y varies between these two lines, minus 2x plus 3 less than or equal to y less than or equal to 3. So the highest possible value of y is always 3, but when x varies between 0 and 1, y varies between this line, the first line minus, so y, where's the line? So y is minus 2x plus 3, so between this line and y equals 3, okay? So that's D1, and D2, here our x varies between 1 and 5, okay? And accordingly, the y varies between the second line and 3. So if you integrate, or if you want to find the double integral using this description, so this is the integral along d1 plus the integral along d2. And I will just write out the two integrals. So on d1, x varies between 0 and 1. So this is 0 to 1, and minus 2x plus 3 to 3. Then 6x squared. So f is 6x squared minus 40y dy dx plus, now x varies between 1 and 5, and y varies between half of x plus half to 3, 6x squared minus 40y dy dx. So these are my two integrals. And now I will make a huge step jump. So I'll just mention after some hard integration computation. And it's completely done on the lecture notes, so I'll avoid this computation. So each one of them is simple. I mean, these are just polynomials involving x and y. So each of these integrals are not hard at all. The final answer is, so I'll just write the final answer, 935 by 3. Once again, I'm not interested in the final answer, rather setting up this integral. That's what is important for me. Okay, so this is one example where you can split up a domain to solve the integral. I mean, this is not a really helpful example in the sense that this exercise, so viewing this as a type 2 region is much easier. But once again, in another example, maybe splitting this up will shorten the time, shorten the computation. Okay, any question about this particular problem? Okay, seems like you are following everything that's going on. So we will end today with the following. So this will be the last problem. So remember that I mentioned if a domain is of type 3, so you can view it as both type 1 and type 2. But viewing it as one type or another is important. Nope. Oh, okay. Nope means you don't have any problems. So viewing it as one type or another is important in the sense that in one type you may be able to solve the integral, while on another type you may not be able to solve the integral. And if you need an actual solution, it's better to view it as a correct type. Okay, I mean, sometimes it's not enough to know that the integral exists, but it's important to solve the integral. So it's important to view the domain of a particular type. So let's see a specific example where this is really important. So we are now on page 10 of VC8. So this is where this example is. So let D be the region bounded by the parabola x equals y square, x-axis, so x equals 4 in the first quadrant. Okay, now find this double integral where f is this trigonometric function. So y cosine of x squared. Okay, so this is my function. Now, this is the picture. So this is the parabola which intersects the line x equals 4. So this is my line x equals 4 at this point 4 comma 2. So this is y equals 2. So this is my domain. Okay, so this is domain D. Now immediately, well, at least for me, it's very easy to view this domain as a type 2 elementary domain, isn't it? I mean, we can immediately view D as a type 2 domain. So y, of course, varies between 0 and 2, while your x varies between y square and 4. It's as easy as that. The x varies between this parabola, y square, and x equals 4. So this is the first instinct, that you view this domain as a type 2 domain, okay? Now, if you try to solve this integral, viewing this as a type 2 domain, let's see what happens. So this is from 0 to 2. Now x varies between y square to 4. Now f of xy is y cosine of x square. So y cosine of x square dx dy. Okay, so this is the integral. Now, if you try to solve this integral with respect to x, you are stuck. So y is a constant, so we don't bother about y. The problem is that integrals of the type cosine of x square dx is not closed. Not closed in the sense that there is not an antiderivative. So you cannot use, although you know that it exists, there is no good antiderivative of this function cosine of x square, which will give you this integral, right? So these integrals, they are not of closed types. You know that this integral exists, but you cannot write down the integral, okay? So we cannot okay? And since we cannot write it out, there's no way to solve this particular integral, and hence you cannot get a particular answer. You know that it exists, but you cannot get a particular answer. Now the way out here is that D is of type 3. So you can view this as a type 1 domain. Okay, so the way out is to view D as a type 1 domain. Okay, so what is the description then? So here x varies between 0 and 4, while your y varies between 0 and square root of x, right? Remember that y square is equal to x. So in the first quadrant, y is the positive square root of x. Okay, so y varies between 0 and positive square root of x. So this is the type 1 description of D. And now we can try to solve this integral as type 1 domain. So x varies between 0 to 4, y between 0 and square root of x. So y cosine of x square dy dx. Now at least you can start off. This integral is fairly simple. I mean, cosine of x square is now a constant. So then this is simply integral 0 to 4 y square over 2 cosine of x square the range being 0 to root of square root of x. So this is the integral that you want to solve finally. So x over 2 cosine of x square dx. Now the presence of this variable x over 2 changes the scenario completely. Now it's a very simple change of variable. So we take u equals x square. So du is 2x dx. So the simple change of formula reduces this problem to a very simple one. So then this integral, is reduced to the following. So 1/4, the range now becomes 0 to 16 cosine of u du, okay? And this you can solve. So this is 1/4 sine of u, 0 to 16. So this is 1/4 sine of 16, okay? So viewing this as a type 1 domain helps you in solving the integral. You can get to a concrete answer, but viewing it as type 2, you are stuck. So that's what I was saying, that viewing it as one type or another is really important in order to solve the integral. Okay, so this is where we end this computational part and today's lecture. My plan was, since I thought that next Tuesday is also, I mean, it's a class day, I thought that I will cover Green's theorem then. But as I said in the beginning of the lecture, so it's up to you. I can pre-record a lecture and upload on YouTube. So you can listen to it and we can discuss maybe next Tuesday or next Thursday, whichever works for you. Or this could be the end of the course. So, I mean, unfortunately, we won't do Green's theorem. So let me know by Saturday what we can do. I mean, I'm good with whatever, either way. So I can give a pre-recorded lecture, or I mean, I can end here. Well, questions about this problem before we end the lecture? So study all the examples or all the problems that are in the lecture note. And I have posted some practice problems, so I'll put solutions of them very soon, maybe over the weekend. I'll put a practice final on Sunday, I think on Sunday. And I'll post solutions of that too, maybe next week, sometime in the middle of next week. Is the final from test 2 through to it's cumulative. It's not just from test 2 through to today, it will be cumulative. The point is that there are no independent questions right now. I mean, if I give you a problem from vector space, you might need to solve a system of equations. So, or you need to solve some determinants to get to the answer. So, I mean, everything is intertwined right now. Yeah. Through to today, so I guess you are hinting that I should end the lecture today and not pre-record anything else. Well, in any case, let me know whatever your choice. You can coordinate among yourselves, and will Green's theorem, if I pre-record the lecture, then yes, it will be on the final. If you, I mean, again, it's up to you. If you want to know Green's theorem, then I can pre-record and I will include it in the final then. If you, yeah. If you already know Green's theorem, then maybe you may not bother. The point with this vector calculus is that I guess most of this are done in Cal 3. So it's mostly a revision for some of you who have done Cal 3. Well, anyway, so let me know about this Green's theorem by Saturday. So I mean, just coordinate among yourself and send me maybe 1 or 2 emails. Don't like send 80 or 90 emails. Just send maybe 1 or 2 with your decisions, and I will do accordingly. I might pre-record or I might end it here. Anyway, so if there are no more questions for the moment, I will end the meeting now. So this is our last synchronous meeting. Hope you have gained at least something. I mean, I always prefer in-class lectures. So this was also something which is not very comfortable for me, but I mean, I tried my best. Anyway, so let's end the meeting. And yeah, it was kind of a distraction for me too. It's a good distraction for me too. Yeah, but yeah, have a good weekend and maybe see you next week. So I'll put some office hours. So Tuesdays and Thursdays. Yeah. Oh, great. Yeah. I'm happy that it's been useful. Okay, so see you sometime next week. Bye-bye. Bye. That's your dog? Nice dog.